Huffman coding is a method of data compression, and just a bit about what data compression is. We need it to be able to store large files. You may have used it yourself with WinZip, for example. So we need to store files in a more suitable file size so that we can store more files. If we haven't got very much storage space, this is something that we really need to do. The two methods of compression, run length encoding and Huffman. I've covered run length encoding in another video. So with Huffman coding, it's a lossless method of compression, which means that on compression it doesn't lose any detail. It looks at the frequency of which data items occur. So for example, E occurs a lot in the English language, whereas Z is used less frequently. And based on that, it gives each data value a unique binary code, shorter binary codes of data values that appear more frequently. So for example, here's a sentence: he sells seashells, and I'm looking at all the characters in there. I'm looking at the spaces as well. So if you can see my table here, I've listed all my characters and I've listed the frequency at which they occur. So H I can see twice, S I've got 5 times, but A I've only got once. So then what I do is I'm creating myself a tree from that, a Huffman tree. So I start to draw out some nodes, and I put each character in there, A, H, space, E, etc., and the number, the frequency at which they occur. So A is once, and the least frequent go on the left hand side, the most frequent go on the right. Then what I want to do is I want to combine the nodes together. So A and H can be combined, and look at the frequency there. 1 plus 2 is 3. Put that back in the tree. So this is an ordered list, so that then goes there. Then I might take the space, the 3, the A and the H there, and combine that. Now I've got 5 because there's 2 spaces and 3 occurrences of A and H. So that goes back into the tree. Then I might want to combine L and E, so they appear 4 times each. So that's 8, that goes back in the tree there. Then I combine these values here. So I've now added my space there, and I've combined that in the tree with the S. So I've now got 5. So I've got the space there, the A and the H, and the S, and that leaves 10, and then I combine the 2 final nodes to leave only 1 node, and that is my Huffman tree. Then what I need to do is I need to label the branches of the Huffman tree. So in my Huffman tree, the branches that go off to the left hand side are labelled with 0. If they go to the right hand side, they're labelled with 1. So you can see my tree here, I've labelled all the branches 0, 0, 1, 1, 0, etc. So it's going towards the left, it's going to the left, it gets a 0. If it's going to the right, it gets 1. So once I've done that, then I can give each character a Huffman code. So let's look at H, for example, down here. So to get to H, it's like think of it like a pathway. I need to go that way, then I need to go that way. So it's 1, 0, then I go that way, then I go that way. It's 1, 0, 1, 1. E is over here, and that's 0 and 0 to get to that. Okay. Space is 1, 0, 0. So if I follow that, 1, 0, 0, here's space, etc. Okay, so what you need to remember is the zeros are going to the left and the ones are going to the right. So finally, using Huffman code to encode the string, he sells, she sells, seashells. Let's pronounce it correctly. It's a real tongue twister that. I don't quite know why I chose that sentence, but just to make it a bit easier for me making this video perhaps. Here's my sentence. Okay, So what I've done there, try to space this out as best I can, but H is 1011, E is 00, space is 100, etc. And for each character I've written down the Huffman code. So if I add up these ones and zeros, I end up with 44 bits. So encoding the sentence in ASCII would need 7 bits per character. So if I say I've got 18 characters there, including spaces, I need 18 times 7, which is 126 bits. So take 44 away from that, and I've saved 82 bits there. So that's working out the calculation for the amount of bits that I've saved, and that's this whole reason to be. It's to save space. So I've saved 82 bits, which might not sound a lot, but actually is quite significant really. If you consider several sentences like that, it starts to add up. So that's Huffman coding.